Bismillahirrahmanirrahim. Assalamu alaikum. I am Engineer Zarif Khan. Today we will discuss in this video about the deflection of simply supported beam. We have shared some videos regarding its cantilever slab and some other important topic. Today I will explain about the deflection phenomena and the deflection criteria as per code. Usually this deflection check is not carried out by engineers. That's why that this deflection occurs in many cases. Today we will discuss about the simply supported beam case. Suppose we have a beam which is supported on walls, masonry walls. This example of the simply supported beam that which is like at the ends we don't have negative moments, just this is free to rotate, but it's like a hinge support and roller support. So that's the example of simply supported beam. We will explain about this calculations, but let me show you all the steps involved in this. The most important thing is that we have to calculate this cracking moment, M cracking, and then effective moment of inertia. So first of all, suppose we need to show or to calculate the deflection in a beam having a span of 25 feet, which is almost 8 meter, round about 7.5 meter, and we have loading live load and super dead load criteria. Suppose we have a wall on this beam which is 10-inch or 9-inch wall. Let's say its load is 1 kip or 1000 pounds per feet. On the beam the load has been transferred, and the super dead load is 1 kip or 1000 pounds per feet, and the live load is 700 feet. This is very important for the engineers to know about how this load comes on the beam. The load comes from the floor and from the super structure like masonry walls and some other machine equipment, etc. So we have to see this one. Like suppose I have taken this 700 pounds per feet. It means 0.7 kip per feet is the load, live load. Then the span is 25 feet. This yellow, I have highlighted this yellow. This we have to feed this data. The other is the length, and automatically it's calculated. 25 feet is the span, and beam width we assumed 15 inches. So this is the assumed one. Let's see this assumption. Actually there is a formula for the depth calculation. This is L by 16. For the simply supported beam we have to adopt as per ACI 9.5a table. So according to this, if we see this is 18.75 inches. So 25 feet, if I convert to inches by 16, so it comes to 18.75 inches. This is the minimum depth we have to provide. Okay, let's suppose we assume this depth as allowed by the ACI. This is the minimum one, but according to the load we have to decide what should be the depth of the beam. Suppose we put this depth 18.75 here, the beam height, this 18.75 we put here, and let's see its results. This is the effective depth, then this is the D dash, the flop. Clear span is 25 feet, it's calculated. Now the concrete unit weight we have to put 150 pounds per cubic feet. This is the concrete compressive strength 3000 psi. or you can say this is 20 kilonewton per millimeter square. This is the strength of tensile strength of steel. Then this modulus of elasticity we have to calculate. This is the formula, that 57,000 into square root of fc prime. Okay, then this modulus of elasticity of the steel, 29,000 raised to the power 6. Then this n we have to calculate. This n is required here in this calculation of the deflection. So where this n come from? This is actually the ratio of these two quantities. This elasticity of concrete by elasticity of steel ratio is n. This n value we will use in the other equation. Let's see. Suppose we provide steel here, number 6 bars in the bottom, and we provide 4 number 6 bar at the top. This is the ratio, the steel area, sorry, and this is the ratio of the steel. This is row and row dash. These are calculated automatically. Okay, this is the first step. We have to put all these properties into how to calculate this deflection of the beam. There is a limit by the ACI that it should not exceed this much deflection, like L by 360 or L by 180. I have put here at the end. But let's see the step 2. Okay, now in the step 2 we have to calculate the load. The live load we have, but the dead load of the beam we have to calculate. This is the dead load of the beam. Okay, the total dead load is DL plus live load. So it's automatically calculated. Then the moment due to dead load is 101 kf feet. Then this is another one, load due to live moment due to live load. This is the combination of both the moments, live plus dead load. This is a combination. And if we suppose there is some sustained load, we can also put that one. So let's suppose this 50% of the live load is sustained and the other is not sustained. Okay, so this we can also take this moment. In the step number 3, we have to see this fracture. This modulus of fracture we have to calculate. Okay, we have this formula, 7.5 into under the root of this is actually linked to the concrete strength. So modulus of rupture, this is one. If all calculated, then this gross moment of inertia, BH cube by 12, automatically calculated. Then this centroidal YT, then this B breadth, capital B, this R, these are some coefficient. This is you are in this formula. We have to calculate this R and this KD. This is research based formula, and we have to calculate this KD. For KD we need this B and R, D dash D. So we have to calculate all this B. Suppose this B is where from? This B is actually the ratio of these two things. Let's see here. This is the ratio of these two. This N is actually the F7 is, we have this F7 by F7 is the breadth of the beam. Okay, and this and the bottom we have taken this other ratio, F18 and F19. So F18 here we see this is the N and this is the NS. Okay, so this is the, we have to calculate like this B. Then R be calculated from here, formula is there. Then this KD, we can calculate this KD from here. Okay, to put all these values, so this KD will be calculated. These are the important features for calculating this M crack or the effective moment of inertia. This M crack is dependent or on this effective moment of inertia. When we calculate this effective moment of inertia, so this is the important thing we have to consider. This then kd cube, okay, in the other formula. This is for the formula. Let me make it large. I crack is equal to B into kd cube by 3 plus n area of steel in the bottom, then d minus kd raised to power square plus ns minus 1. This is the top steel, and then kd minus d dash square. This formula we can use, and for this we need this kd, this square, this square. So I crack can be calculated here like this. So this automatically for I will share this sheet in the comments and in this video when I share this video. So don't worry that I will share this whole sheet with you. So you can just put the values and it will be calculated. Then the ratio of the gross moment of inertia and I crack is 2.17. Okay, these are the important features we have to calculate in the deflection calculations. Once these are calculated, then it is very easy and very simple to calculate the deflection, because in the deflection we have some certain values. Suppose this is the deflection equation for the dead load, K into 5 by 48 into M dead load by this other factor EC. Okay, so these properties we have. The important is this, the K, from where the K will be for simply supported beam, this K will be 1. Let's go up and we see this step, another one, this step 1. Now M crack is from here. This is the M crack. You can calculate easily. It's automatically in the formula. Then this M crack by M dead load. For the dead load, if we just consider only the dead load, so for only dead load, this we have to find this ratio. If this ratio is more than 1, it means that the gross moment of inertia will work. So no need of calculating the effective moment of inertia. So I have put this check on this. If suppose this value is greater than 1, then take suppose, let's see if this is, I put here 2, suppose this will change. Okay, take IE dead is equal to IG. So here I will put this IG, but suppose here this is 0.3. So 0.3 is actually less than 1. So we will take this effective moment of inertia. Okay. Okay, this is done. Now this is this M crack sustained load, for sustained load only. This is 0.01. This is I sustain, this one. Then M crack by dead plus live. This is the combination for dead plus and live load both. This is the case. So the effective moment of inertia is calculated for all the cases, and let's see at the end where we can use this one. This I effective I will be used in the equation of this deflection. So this step number 5 is the calculation of deflection. Deflection, we have this simple formula for the deflection. So 5 by 48 md L square by EC into effective moment of inertia. So here calculated deflection is 0.92. Okay, this is the sustained load deflection 1.19. Okay, and this is the dead plus live load deflection combine, and this is only 0.53 deflection due to live load. Now these are the calculated deflection in this beam. So due to moments of dead load, sustained load, dead and live load, and live load, the deflection will be up to these inches. 1.46 inches is the maximum one. Okay, so we have to compare this deflection with the limit of as per ACI. So let's see the check. These are the checks. Okay, suppose we have this criteria that for live load deflection L by 180, it should be 1.67. So the beam section is safe for the live load. But for both the cases, if suppose this is the live plus dead load, another criteria length by 360, so it comes to be 0.83. So these four values must be less than 0.83. Okay, because the beam, the length of the beam is 25 feet, and this for this much length, sorry, the deflection must be 0.83. So it shows that revise the beam section. This is a check. That suppose here is the section is safe, but here in this criteria, if you see this criteria, so this is not governing. Now because we have assumed the ACI this depth. So ACI gives you the minimum depth. It will work, but maybe for the small load, suppose I revise this 500. Okay, let's see now the effect of this load. What will happen? The beam is safe or not? Still revise the beam section, that even if we revise the live load, the dead load, so still it is 0.83. This is okay, this is okay, but here it's not okay. Okay, so here we have to reduce this deflection. For this, what we can do? Deflection is actually associated with the two properties: the width and the height of the beam. Either we have to increase the width or we have to increase the depth. We assumed this 18.75 due to this criteria by ACI. Let's make it 20 inches. If we make it 20 inches, let's see now at the end the result, that is it safe or not. Still it says that this is 0.92 and this is 0.83. Still we are not safe. The beam is not safe here. Revise beam section. Okay, so 20 inches do not work. Now let's see, this is 21 inches. Let's see, I have reduced this load as well. Okay, 21 inches. Let's see the result, what happens. Now the beam is safe. Okay, this is good. That if we provide the beam depth, this beam depth is actually including the slab, the total depth. Okay, so it should be at least 21 inches. Okay, if 21 inches is the beam depth, so it means that this is this is excluding the slab. Okay, the depth 21 inches will work, but the beam is safe here. But another issue we face, that we have reduced this load. Okay, if I increase this load to suppose 700, let's see now its effect. What will happen? The beam is safe or not? Now this give you the revise the beam section, because with this load it will not work. Let's suppose I make it 1000. Okay, so with 1000, let's see at the end it will work or not. If it's not working, it means that there is the same revise the beam section. Okay, so this is the live and the dead load is 1.1. okay, this is 0.9. This criteria is okay, this deflection is okay, for dead load is okay, for sustained load no. For dead live, no. For live, it's okay. So we have to design the beam for the live and dead load combined. So 1.1 we have to satisfy this criteria. So revise the beam section. Okay, let's see, and we increase the beam section. This is 21. Let's make it 24 inches. If we make it 24 inches, let's see now the result, what happens. Now the beam is section is safe. It means that if we design a simply supported beam having 25 feet length, and we have this loading criteria, 700 pounds per feet live load and 1000 pounds pound per feet. So the deflection will be controlled only if we provide a beam of 15 by 24 inches. Okay, so a beam of 24 inches will work, and only this we can make it. Like suppose this is a beam and we make it simply, so this should be I say 24 inches, and this should be 15 inches. It will work. Okay, so I think it's clear now how to calculate the deflection and how to check it. Okay, so this is a simple procedure. I will share the sheet and you can use it easily. It's available online, and thank you for watching this video. You can edit this anytime for your own. You can change this loading criteria, you can change this length. Suppose I make it this 30 feet. Okay, so let's see the result. What will in the 30 feet? 30 feet the beam is not safe. Revise the beam section. It will give you, because 1 inch is the criteria. Okay, according to the it should be less than 1 inch. This criteria. Okay, so 2 inch is L by 20. So here if you see this is 1.3, 1.6, then you can come here and you can make it. Suppose this is 24, make it 27 inch. Let's see what happens. Still this is the issue. Suppose make it 30 inches. Now the beam is safe. Okay, this is less than 1, less than 1, less than 1, and okay, now this is satisfied. All are satisfied. So it means this another very important to note this point, that if an engineer do not have the idea, he should provide a beam depth at least 1 inch for 1 feet. Suppose the beam length is 10 feet, he should provide at least the depth 10 inches. If the span is 15 feet, he should provide at least the depth 15 inches. This is a thumb rule, like I'm sharing with you. Most engineers start with this one, but like the competent engineers, they calculate, and the experienced engineer, they calculate and they see that maybe small section will work, because depends on the load. Some time there's too much load, so maybe a deep section will work. Sometime there is a small load, so like small section will work. Depends on the calculation. But for like a foot for thought and a thumb rule, you can provide the beam depth at least 90% of suppose 90% of the in inches of the span. Okay. Oh, thank you so much for watching this short presentation, and we will be sharing more important videos regarding this design. Let's see. Please share your comments and share your valuable remarks. If you have some suggestions, some good knowledge, we can learn from each other. Thank you so much, and Allah Hafiz.